So next we're going to take a look at some more gas law problems. So the next one we'll look at is how we're going to calculate gas density. There's a couple ways to do this. So first we have to remember density is in gram or mass per volume. And in this case, we're going to use grams per liter. Most substances, we report density in grams per milliliter or cubic centimeter. Since gases are not so dense, we're going to report them in grams per liter. So one method to this is first we're going to find the moles in a liter of gas. We're going to convert that to grams, and now we have grams per liter. So let's take a look at our problem. We'll go ahead and solve it this way. So what our goal is to calculate the density of helium in grams per liter at 21 degrees Celsius and 752 millimeters of mercury. So here's our pressure, our temperature. We will, of course, need to convert into Kelvin. So go ahead and do that with me. Okay, so it's going to be 294 Kelvin. All right, I'm trying to find the density of helium. And like I said, first thing we want to do is try to find moles of helium. So I've got temperature, I have pressure, but we're missing a couple things. If we take a look at our ideal gas law, PV equals nRT, you can see that I'm missing volume, okay? It does not give us a specific amount. So what we're going to do is we'll just say, let's assume that our volume is equal to 1 liter. Okay, so we're going to find out how many moles we have in 1 liter of gas, and then we'll go ahead and go from there. So you're given pressure in 752 millimeters of mercury. You have a choice now. You can convert that to ATMs and use the gas constant in ATMs, or since your equation sheet also gives you the gas constant for torr, and torr is equivalent to millimeters of mercury, we can go ahead and do that. So let's go ahead and use that method. So we take a look at our equation sheet. It tells us that R is 62.36 liters times torr over moles K. Okay, and like I said, our pressure is going to be 752 millimeters of mercury. Our temperature in Kelvin is 294. Okay, and then we're going to go ahead and find moles right now. Oh, and then we're assuming a volume of 1 liter. And you want to make that exactly 1 liter. So put as many sig figs as you want on that guy. So go ahead and start solving this problem. Feel free to put me on pause right now and try it on your own, and then unpause it and catch up. Or let me catch up with you and make sure that you are good to go. Okay, so I'm just going to multiply my pressure times volume, and divided by R, which is 62.36. Again, this is torr, which I'm actually going to write here as millimeters of mercury, so things cancel out nicely. Remember, torr and millimeters of mercury are exactly the same thing. They're equivalent. I'm going to put my temperature in there. Okay, and now we should see that temperatures cancel, liters cancel, millimeters of mercury cancels. We're left with moles in the denominator or the denominator, so we're going to kick those up. And so we will get for our number of moles, 0.04102 moles. And next thing I want to do is double check my sig figs. So I take a look here. I've got 3 sig figs in pressure. Actually, I have 4 sig figs for my R. I'm good there. I've got 3 sig figs in K. Volume, redefine that. Pick as many sig figs as you want. So we're going to round this guy to 3 sig figs. So I'm just going to underline that third digit there to indicate that that's our last significant digit. That 2 is not significant. I can cut it off now or just leave it and just keep track of my sig figs in the end. And that's exactly what I'm going to do. Okay, so now remember for density, for density, we're going to have we need density in grams per liter. We've already said that our volume is going to be 1.0 liters, so I need to get mass there. I don't have mass, though. I have moles. How are we going to get mass for moles? We're just going to use our molar mass and dimensional analysis. Okay, so I've got 0.04102. Again, that O is our last significant digit. Moles of helium. And then we look up on the periodic table the mass of 1 mole of helium, and that is going to be 4.00. Okay, plug and chug. I got 3 sig figs over here. I've got 3 sig figs over here. So our mass will end up being 0.16488 if you don't round. Okay, and then again, we do want to check sig figs. We're going to have 3 sig figs, so it's going to be 0.165. So that's the mass in 1 liter of gas, and so that's really going to be my density. So I want to write that out, though, that density is mass over volume. And so we're going to have 0.165 grams of helium over 1.0 liters. So my density of helium is 0.165 grams per liter. Okay, and that's going to be my final answer. But the last part of the question asks us about the difference in the mass per liter of helium versus air, because that's going to be proportional to the buoyancy, the buoyant force, basically why helium balloons rise in air. So what we can do is take the density of both, which is in per liter, and say in 1 liter, we've got the mass of air is just going to be 1.188 grams. Okay, and I just got that from the problem because it said the density of air is 1.188 grams per liter under these conditions. We're assuming 1 liter. And then the mass of helium we just found is going to be 0.165 grams. I go ahead and find the difference, and that's 1.023 grams. Okay, so that is one method to go ahead and solve for the density. Another method would be to do a little bit more algebra first. Okay, so I'm just going to introduce this method, and you can choose to do this method or not. So I've got my ideal gas law, PV equals nRT. Okay, and we also recognize that molar mass or molar weight is going to be equal to the mass divided by the number of moles. Okay, so now I'm going to rearrange this to solve for moles. Okay, our number of moles is equal to the mass over the molecular weight. And now I'm just going to do a little substitution. So PV equals mass over molecular weight times RT. Okay, now I want to rearrange this to get density. Okay, density is just mass over volume. Okay, so let's rearrange this equation to get mass over volume. So in order to do that, first let's just go ahead and get rid of all of our denominators just to clean this up a little bit. You don't have to do this step. You can skip it if you're able to. Okay, so I've got mass over here. I want to get mass over volume. So I'm going to divide both sides by volume. Okay, so that gets rid of volume. Now I want to get rid of RT over here, so I'm going to divide both sides by RT. So I end up with mass over volume equals pressure times molecular weight over RT, and that is equal to our density. Okay, just by doing a little bit of algebraic manipulation ahead of time, we can get one algebraic equation that we can just plug and chug our values into. Okay, so this way overall ends up being a little less work than the previous way, but it does require a little bit more algebraic understanding on your part. Okay, so go ahead and give that one a shot. Feel free to try this out. Plug in the same numbers. You should get the exact same answer in the end.